Here what we're going to do is solve the circuit on the board using the node voltage method that we just introduced in the last section. So in this particular problem, what we're really trying to do, if you were to see this kind of thing on a test, is you would be presented with a circuit like this, and it might say, find V1 and find V2. Find those two voltages. Now, it may not even tell you to use the node voltage method. That's something for you to decide. You could use Kirchhoff's laws, Kirchhoff's current law, Kirchhoff's voltage law to do this. However, I think you can see that it's got a lot of interconnections and it would probably lead to a few equations here. So it's certainly going to be easier to use the node voltage method here. So what we're going to do first is identify our essential nodes, and we'll do that right now. Well, right off the bat, we see that this node here is already an essential node because we have the current source, the resistor, and the other resistor. We have 3 or more connections, so that is an essential node. All right, we see we have a giant mega node at the bottom here. They're all basically connected together, so this is one giant essential node at the bottom. If it helps you, you can put these dots. You don't really have to put these dots. And then over here, you might be tempted to say, well, here's a node and here's a node. But here is sort of like where circuits can get a little tricky, because when I show you simple circuits, then you might make that conclusion. But then you need to realize these things up here, they're all connected together. Even though they're drawn far apart like this, this resistor is connected to this resistor, which is physically connected to this resistor through a perfect wire, which is also physically connected to this current source through a perfect wire. When there's nothing in the way, if it's just a perfect wire, then they're physically joined together. It's like if you were to solder it together, they would all be joined at this common point up here. Of course, the circuit would look ugly to join them like that, so we draw it spread apart. But this is basically one big, interconnection up here. So for the purpose of keeping track of it, I'm going to put the dot here to represent that there's a node there. Mostly the reason I'm putting it there is because we're interested in finding V2 voltage. But I want you to understand that when we write our equations, all of this behaves as one giant node. It behaves as one essential node up there, even though it's drawn kind of spread apart. It's all connected together. Okay, so when we step back and look at it, what are we trying to do? We're trying to find V1 and V2, but look at how things have been lined up. V1 just happens to be the voltage of one of our essential nodes. V2 just happens to be the voltage of the other essential node. And if you notice at the bottom, there's an essential node down here. It makes sense to then treat this as the reference node. Why does it make sense? 2 reasons. One, it's at the bottom of the drawing. Most of the time, the references are going to be at the bottom. Number 2, it's got the most number of interconnections, the most number of things joined at one point. That's kind of a good rule of thumb to use your reference at that point. Number 3, V1 and V2 are already defined so that their negative sides are kind of common at the bottom. So it makes sense that our reference is going to be at the bottom of these voltages here. So that's kind of a no-brainer. So when you do your test, do yourself a favor, mark your nodes down, mark your reference down. At least if your equations are wrong, you can get some partial credit by doing a good job with outlining what's supposed to go on here. So now we need to turn our attention to actually making the node voltage equations. Now, just to make it even easier later, let's call this essential node number 1, and we'll call this one essential node number 2. Notice we have 3 essential nodes in this drawing. We have the one here, we have the giant essential node at the bottom here, and we have this node over here that's really a giant interconnection. So there's really 3 essential nodes, right? That means we're going to need 2 node voltage equations, just like we did in the last section. So pretty easy. 2 equations, 2 unknowns. We're going to get the solution straight out. All right, so let's start off by, let's find the equation at essential node number 1, the one over here. Okay, so again, the point of it is, here's the essential node. We want to sort of pretend that current's going out this direction, current's going out this direction, current going out this direction, and we're going to sum all of those currents to be 0. So right off the bat, we have a current source going in, but that's okay, because if we're pretending the current's coming out, it just means that that's a -6. If this current source were pointed the other way, it would be in line with what we're trying to do, and we would have it positive. But since we know 6 amps is coming in this direction, we're going to treat it as negative. Again, in the beginning of this course, in the beginning of the entire circuit analysis sequence, I told you that sign convention was so important in circuit analysis, and it continues to show itself over and over again. You need to know that for each essential node, you're trying to write the current as it flows away, right? So therefore, if current then is known to come in, it has to be negative. If you forget about those sign conventions and kind of halfway know what you're doing with node voltage, you're going to write the wrong equations. If you have a positive sign here for the 6, you will get the wrong result, and you'll get basically the entire problem wrong for a simple understanding that you could have had. So this is the current in this leg. What is the current through this resistor as it were to flow away from there? Well, I is equal to V over R. The voltage across this resistor, whoops, this is not an equal. This is a plus, so we're summing everything up. V over R, so it's V1 over 40 ohms. V1 over 40 ohms. And that's already set up in the proper direction, because if the voltage were really like this, the current would indeed flow down. And we've talked about that before as well. When you have a voltage across a resistor, the current's going to flow from positive to negative. Okay, plus. What is the current as it flows through this resistor as it flows away? Well, you need to know what the resistance is, or what the voltage is across this resistor, and we figure that out by subtracting our node voltages. So it's going to be V1 minus V2 over 8 ohms. That is going to be equal to 0, because now we have this current minus 6, this current here, this current. Let me take a second to show you. Don't forget, what we have over here is V2. This voltage is the same as the voltage across this guy, which is the same as the voltage across this guy. The reason is because they're all connected in parallel. So they're all connected by perfect wires. So V2 is the same across all 3 of these elements over here. So if I'm trying to find the voltage drop across this resistor, it's going to be V1 minus, remember this is the voltage here, minus V2. Then I've gotten all the way back down to my reference. V1 minus the next voltage that I can find that comes down to my reference point. The difference between these voltages is going to be what lies across that guy. The reason we write V1 first is because we're pretending that this current comes out of the node, so we have to pretend V1's bigger, V1 minus V2. So again, rule of thumb, you're working on this node, pop up to this node first, minus any other voltages. That's going to give you the proper direction. V1 minus V2 is the voltage across that guy. All right, so that is equation number 1 at that node. The other equation at node number 2 is going to be a little, I won't call it tricky, but you got to think about it. Because remember, node 2 is really the interconnection of all the stuff up here. So really, when we're trying to find the current, we're trying to find everything as it goes away. So first, we need to figure out what's the current. Remember, they're all joined together. All of this stuff is joined together at one point. So we want to find out what's the current going through the 8 ohm resistor, then through this resistor, then through this resistor, then through this current source. The current through the 8 ohm resistor is going to be, pop up to your node voltage, V2, minus this node voltage, V1, over this resistance, 8. Because we're taking the voltage difference. The voltage here minus the voltage here is going to give us the drop across the 8 ohm resistor, pretending the current is going this way. V over R is going to give us the current. So that takes care of this guy. This guy here, so I have a plus. V sub 2, as it's written here, is the same voltage as is written as it would be across here, because they're in parallel. So it's V2 over 80. Plus the current through this guy is V2. I is equal to V over R over 120. Here, the current coming out, it's already drawn as if the current is coming out, so it's just a plus because it's going out. 1 amp equal to 0. And that is the equation. Make sure you understand that. We need to write the current flowing out of this giant node. The current going through here is this voltage minus the voltage here. That gives us the voltage across 8 divided by 8. I is equal to V over R. I is equal to V over R here. I is equal to V over R here. And then we know what the current is here. This is another great example of how you have you have to have good fundamental grounding in these principles. Because if you see on a paper that V2 is the voltage across this 120 ohm resistor, you have to know from your experience that this voltage is the same voltage that's across the 80 ohm resistor, because they're in parallel. So that's why everything builds on each other in circuits. You have to get that kind of like understanding, because the way it's drawn is this voltage is across here. Well, I didn't tell you that was the same voltage here. You have to know that because you have to know what parallel circuits are, which we've covered in the past. All right, so the bottom line is we have two equations and two unknowns. And the problem with node voltage, here, let me take the ohm symbol off here, you don't need that. The problem with the node voltage method is that you're always going to get equations with fractions. Just get used to it. All of them are going to have fractions because you're going to have V over R everywhere. And it gets ugly. So a lot of students, when they see an equation like this, they kind of struggle because they have all these fractions and they don't know what to do. My advice is eliminate the denominators. Basically, just get rid of them. Don't forget, these are equations. You can do anything you want to them. I can multiply this equation by 9 million if I want to, as long as I do the left and the right side. I can divide this equation by 25 or multiply it by 1.7. It doesn't matter. It's going to still be valid as long as I do to both sides. So that's sort of the methodology I'm going to take when we begin to work with it. So let's take this equation here. What I'm going to do with this equation is multiply both sides of this equation by 40. Why do I want to multiply both sides of this equation by 40? Multiply by 40. Because I can see right away, if I multiply by 40, it's going to eliminate this denominator. 40 divided by 8 is 5, and then 40 times 6 is 240. So I'm gonna have big numbers, but I'm going to eliminate the fractions, which is going to be nicer to work with. So 40 times 6, or negative 6, is negative 240. All right. 40 times this term is going to be plus V1. 40 times this term is going to give me, because 40 divided by 8 is 5, I'm going to have 5. Don't forget your parentheses, V1 minus V2 is equal to 0, because 40 multiplied by 0 is 0. All right, and so then, just to kind of clean it up a little bit, I can say negative 240 plus V1 plus 5, V1 minus 5, V2 is equal to 0. I'll just change colors one more time. Let's write it in terms of V1 and V2. So what I have here is 5V1 plus V1, which gives me 6V sub 1, all right, minus 5V sub 2, right? And I have negative 240. Let's go ahead and move it to the other side of the equal sign, positive 240. So I want to sort of circle this, for lack of a better word, because it's one of my two equations. Notice this equation is very nice. 6V1 minus 5V2 is equal to 240. It's much better than dealing with all these fractions everywhere. So that's kind of what I'm going to request that you do all the time. What we're going to do for this guy here then, okay, let's just go ahead and take this guy down here. All right, is we want to multiply by 120. That's just what comes to mind first, just because I have 120 here. So let's multiply by 120. And so what I'm going to get, when you have 120 divided by 8, you're going to get 15. So you're going to have 15, don't forget your parentheses, V2 minus V1. All right, and then when you multiply 120 here, 120 divided by 80 is 1.5, so you have 1.5 V2, okay? And then here you multiply by 120, so you're just going to have V2 by itself, right? And then you have 120 times 1 is 120, and the right-hand side is equal to 0. All right? So we multiply by 120. This looks pretty good. Let's go ahead and copy it again over here, just to make sure that we've got everything going on. All I'm doing is recopying the previous line. 15 V2 minus V1 plus 1.5 V2 plus V2 plus 120 is equal to 0. Now you could work with this, but I still don't like having a decimal there. That's just a personal preference. So now what I want to do is multiply by 2. Because I know if I multiply both sides of this top equation by 2, I'm going to eliminate, because 1.5 times 2 is 3. So let's go ahead and do that. Let me switch colors real quick. 15 times 2 is 30. V2 minus V1 plus 1.5 times 2, 3V2. 2 times this, 2v2, 2 times this, 240, 2 times 0 is 0. So here is my equation, and keep switching colors to make it a little bit clear. Now we do the distribution. 30 v sub 2 minus 30 v sub 1 plus 3 v sub 2 plus 2 v sub 2 plus 240 is equal to 0. Now I'll switch back to black because I think I'm pretty much going to have the final guy here. Let's sum all the v1s together. Here's a v1. There's no other v1s anywhere, so it's negative 30 v sub 1. Then we have v sub 2s. Here's a 30 v2 plus 3 plus 2. So 30 plus 3 plus 2 is 35 v sub 2. So that takes care of all of these terms. We have a 240. We're going to move it over, negative 240. This is the second equation. And that's the second equation. So basically, what we want to do is we have an equation here in v1, v2, and we have an equation here in v1, v2. And that is basically going to be the gist of the problem. So let's go ahead and move over here and do the final solution. The two equations we're trying to solve that we just wrote down, 6v1 minus 5v2 is equal to 240. The second equation we just found on the other board, negative 30v1 plus 35v sub 2 is equal to negative 240. Now, doesn't this set of equations look a whole lot better than this? I mean, somehow, if you could figure out how to solve this, I mean, you may have a calculator that you can dump these equations in and get v1, v2. If you do, and if your professor is fine with it, then just do it. I mean, there's no problem with just solving these guys. It's just that most of us typing it in and getting it all formatted right may take longer than it's just worth just to simplify it down to something that's nice. Plus, a lot of professors are going to want to make sure you know what you're doing and that you can solve a system of equations. So there we are. And so what we're going to do is set this up as a quick matrix. So don't forget, matrix, the way you write it is AX is equal to B, where X is really what we're trying to solve for. So in that form, the A matrix is going to be 6, negative 5, negative 30, and positive 35. The X matrix is going to be V1 and V2. And the right-hand side of the equal sign is 240 and negative 240. And at this point, it just becomes a matter of entering it into your calculator. So what we have, we know now that X, which is what we're trying to solve for, is the inverse of matrix A times matrix B. So the inverse of this matrix times that one is going to leave us with what we're trying to find. So finally, V1, V2, which is what we're trying to find, is going to be the inverse of matrix A. If you type this matrix in the calculator, hit the inverse button, you'll get 0.58, 0.083, 0.5, 0.1. That's the inverse of matrix A times 240, 240, and negative 240. So we have this guy, we have our inverse set up properly, and so at the end of the day, V1, V2 is equal to, you take this matrix times the one we just have there, and then you'll get something really nice which tells you you're doing something right. 120, and you'll have 96. And you just read it like a book. What it means is V sub 1 is equal to 120, and V sub 2 is equal to 96, and we're solving for voltages, so these are volts. Don't forget your units there. So V1 is 120 volts, V2 is 96 volts. So those are the node voltages. This problem aligned itself really nicely with the node voltage method because we're asked to basically find the node voltages in the problem. It's not stated that way, it just happens to line up that way. You have V1, you have V2. You look at this and you realize, well, this is an essential node and this is an essential node, and these are the node voltages that I would find in the node voltage method. So we write our first equation. This current's coming in, so it's negative. This current is going like this, so it's V over R. This current is V1 minus V2, because that's the voltage here, over R. Again, summing up the currents coming out of that node. Here we sum up the currents coming out of node 2. we have to be careful because there's lots of interconnections here. So when we talk about, we're almost talking about the whole entire node here. The current going through the 8 ohm resistor is V2 minus V1, that's V over R. The current going through here is V2 over 80. Current going through here is V2 over 120 for V over R. And then this guy is just 1 amp. The way it's drawn, it's positive because it's coming out. You can solve the system equation any way you want. I choose to get rid of all the fractionals. So I multiply by 240 and simplify, and I get this. I multiply this. I just choose 120 because it's nice and easy. But then once I get here, I realize I still have 1.5. I don't really like carrying it around. You can, though. There's nothing wrong with it. So I'll multiply again by 2 to get whole numbers for my second equation. Once you have your second equation, your 2 equations in place, again, you can solve it any way you want. You can do substitution or anything you want from algebra. I choose to form a matrix, coefficient matrix, and a matrix on the right-hand side, and basically take the inverse of the left and take the inverse of the right, multiplying through, and you're going to solve for the 2 voltages that you need simultaneously. Now, this problem just asked you to find these voltages, but again, the node voltages are the only thing you need to completely describe the circuit. So if, for instance, this problem said, what is the current through the 80 ohm resistor? Well, now you know, because it's just V over R. V2 is known, and so we calculate that. We can find the current through here because we know what V2 is, V over R. We can find the current through this resistor because we know what this voltage is. We can find the current through the 8 ohm resistor because we know the voltage across this resistor is V1 minus V2. That's going to be the voltage across the resistor. V over R gives us the current. So I'm trying to show you, even though we're not solving for some of these things, that once you have the node voltages, you can find everything else in the circuit with subsequent calculations. So that's why I'm saying we've done a couple problems now in node voltage, and I'm trying to show you that it's a little more rigid and a little more well-defined what to do. Find your essential nodes, find your reference node, label your node voltages, write the node voltage equations, solve them. It's kind of rigid, but you only need 2 equations to solve a circuit like this. If you use Kirchhoff's laws, it's going to take more than 2 equations. You have to think a little more. Do I need Kirchhoff's current law, Kirchhoff's voltage law? It's a little more ambiguous in what you do, and you have a little more freedom, but it takes usually more equations. So that's how you solve this node voltage problem. Follow me on to the next section. We're going to continue ratcheting up the complexity. We're going to do quite a few of these node voltage problems because they're central for these types of circuits, and also later when we get to AC circuits with capacitors and stuff, you'll see that it's very similar with some changes. So we need to make sure and master this now. So make sure and work this problem on your own. Make sure you understand it. Follow me on to the next section and we'll keep practicing.
Learn anything at mathandscience.com.